short non-malleable codes from related key-secure block ciphers, joint work between Serge, Fer, Pierre Carwan, and Mark Manick, and Pierre will do the talk.
Thanks, Bart. Okay, so I'll start with a quick introduction about non-malleable codes. What are they and what we actually want to build. Then I'll present our construction and give a brief idea of why it is a good construction and why you can prove that it works. So non-malleable codes, well, it's quite simple. You just have encoding, decoding, and the encoding is randomized but unkeyed. So you can think of it as being, for instance, similar to salted hashing. So you have a random thing, and then you do an encoding, and well, we have two requirements for this encoding-decoding pair. One is for functionality. We want the encoding to be invertible and the decoding to be the inverse. And then we have non-malleability security requirement, which is basically that if I take two messages M0, M1, then I encode with some randomness. I apply a tempering function that comes from a certain tempering space, mathcal T. Then I decode. Then it should be hard for an adversary to know if I did this with M0 or M1. So in other words, I can define those two distributions of decoding the tempered of encoding of M0 and M1, and those distributions should be indistinguishable. So those non-malleable codes, or NMCs, were introduced by Zimbowski, Pitzrak, and Blix in 2010. And one of the motivations for that was to apply this to tamper-resilient crypto. If you think about the functionality that they bring, it's kind of natural, at least for some fault models. So, for instance, if you assume that you're performing some computation with a tamper-prone memory, let's say some RAM, and you have a tamper-proof circuit where you can do the computations, then if you want to implement crypto on such a device, and if you have a secret, what you can do is that before storing it in the tamper-prone memory, you first encode it with a tamper-proof circuit, then you store this encoded version, and when you retrieve the circuit before the secret, before using it, you just decode it. And so then what happens is that if there was some adversary that injected a fault on the encoded secret, when you decode, you get something that is completely unrelated with what you had in the first place. So then you can run whatever algorithm you want, and whatever happens will be independent from the original secret. So maybe it's going to be completely useless as a computation, but at least it will not reveal information on the original secret. And of course, if there was no fault originally in the memory, then when you decode, you have the secret, everything is fine. So that makes quite a sense in this context. Of course, it doesn't capture all of the fault models, so if you can inject faults on the computation, then it's less clear that this is actually useful. But on the other hand, NMCs are quite popular in some other crypto communities, especially theoretical ones, because they have quite a lot of applications. And for instance, the kind of non-malleable code that we build in this work can be used in a scheme by Goliath et al. To build non-malleable commitments that are quite efficient. So what we do is that we propose an NMC construction that has short code words. So the code word size is the size of the message that we want to encode, plus 2 times the security parameter. So for instance, 2 times 128 if you want 128-bit security. And this construction only relies on a block cipher as a primitive, and what we need for this block cipher is to be relatively secure and also to have graceful single key security degradation. So I'll come back to this, but it's very simple. Notion is just means that if you take a block cipher, you restrict the key space to some large subset of the key space, then the result is still a good block cipher with the accordingly smaller key size. So I think this is a result that shows that related key secure ciphers are a useful primitive on their own. So related key security is not just a nasty, powerful attack model for adversaries, but if you have such a primitive, you can actually also use them for constructive purposes. So actually, we already knew that kind of, because if you have a related key secure cipher, you can use it, for instance, to build a tweakable block cipher, at least up to the birthday bound, but this is kind of an independent orthogonal justification. Okay, so before presenting the construction, I'll just say a few more words on NMCs. So the first is that the tampering function that are allowed by the adversary, actually we need to put some restriction on them, because otherwise, well, if you don't do that, consider, for instance, this function that just takes a code word that decodes it, adds 1, and uncodes it again. Well, then when you decode, you get as a result the original message plus 1. And of course, that's strongly correlated with the original message, so probably the two distributions I showed will not be indistinguishable. So then you need to restrict those tampering functions, and one way to do that is quite nice, is to just allow anything but on two parts of the code word. So we assume now that the encoding, it outputs a code word that is made of two halves, one not necessarily the same size. And the tampering can do whatever it wants on either part of the code word, but independently. And if we restrict to this kind of tampering function, then we can have constructions with non-trivial security, either computational, like what we're doing, or information theory. And how do you measure or characterize the complexity, the security of a non-malleable code? Well, to do this, you can use first a tampering experiment, which is basically just you take some message, some randomness, you encode and you apply the tampering, and then you decode. And we just need a slightly tweaked decoding, because if the tampering didn't do anything, then we're not really outputting the message back, but just some magic symbol that says nothing happened. And in this way, we can really say that if you do this tampering experiment with the identity tampering function on two different messages, then as output you really get the magic symbol both times and not, let's say, M0 and M1, which might be different. But that's just a technical thing. And well, with this tampering experiment, you can define an advantage function for an NMC, which is well, the distance between the tampering on the M0 and M1, the maximum over adversaries, any messages in the tampering function. So kind of classical. And one last remark before going to the next part, that somehow you can contrast non-malleable codes with classical error-correcting codes. So on one hand, with an LMC, you can have something that is functional even if you allow very like ultimate error patterns where actually the error is just giving the zero code word. So you cannot really detect, well, with the classical error-correcting code, if you have such powerful errors, you cannot really do anything. But on the other hand, the requirement of the NMC is that if you cannot correct the error, then the decoding must really be something related with the original thing, so it's kind of a catastrophic failure of the decoding. You don't get something that is even close to what you originally had. Okay, so what's our construction? It's pretty simple. So as I said, we need a block cipher, let's call it E. It takes kappa bit keys, and M1 messages from this M space. I don't really care if it's what it exactly is. Then we can define well, what we call RKMC construction based on E. Well, basically the encoding is we just take the message, and we take a random key for the block cipher, which will be the randomness for the non-malleable code. This randomness, we just output it straight as the left part of our code word, and the right part of the code word is the message encrypted with this randomness. So you have a picture, and the decoding is quite obvious. You just retrieve this randomness, you use it to invert the block cipher, and you get M back. And what we show that in this split state tampering model that I mentioned, where the two halves are quite obvious, then this construction provides kappa 2 bits of security if E is good, and we'll see what it means. So there was some related work with also similar looking constructions. So the previous best work for to build this kind of non-malleable code was by Kiadas et al. 2 years ago, and they also have well, a left randomness, which is now made of K and R, so it's a kind of two-part randomness. And on the right half, it's also the encryption of the message with an symmetric encryption scheme. And then there is kind of an additional hash function that checks that nothing was tampered to match. And then the code words are, well, they have different instantiation of the scheme, but for instance, M plus 18 kappa or N plus 9 kappa plus some logarithmic factor. And they prove their construction under key A with the CRS, more about that soon. And actually this construction can also be seen as a refinement of a previous construction by Lisanskaya in 2012, where they do basically the same but in a public key setting. So now we have a secret key for a public encryption scheme on the left, Then we have this public key, the encryption, and some non-interactive zero-knowledge proof. And so now the code words a bit longer, the length is quadratic in the security parameter, and the proof uses a CRS. So what are key and CRS? It's not a mountain parrot from New Zealand and a French riot squad. It's actually for key and knowledge of in the exponent assumption. And this is not so nice actually, because, well, it's not really the standard model because it's not falsifiable, as shown by now. And CRS is a common reference string. Basically means that before defining a string, you need a trusted setup to generate, for instance, public key parameters. And you can implement that with ceremonies. You might have seen some for some of the fancy cryptocurrencies. Okay, but we don't need that, so that's good for us. So now, why does this work? So first, I'll actually show what doesn't. We see even Monster Cipher just in the previous talk, and those are really, really bad to instantiate our construction because they have very bad related key security. At least if you just take the original scheme, where you just take the message, you have the whitening input key and whitening output key. And when the single key setting, this is proven secure in the ideal permutation model, but it has a very trivial and powerful related key distinguisher. If you just take an offset function that you apply to one of the key and to the message, then when you encrypt with even Manso, actually you get the same as without the offset. Or you can do the same with the encryption. And there is a very simple way to explain that with a picture. Well, I have my input x, I add delta to x and to the key, because the key is just XORed to x, I have nothing, so I have no input difference to my permutation, and then nothing to the end. And you can do the same also if you have the same key for the single key, even Manso variant, then you just get, y plus delta at the end. So what are the consequences of this distinguisher if you use even Manso in our non-malleable code construction? Well, then for the tempering, you can use a similar offset function. And basically, what you get at you temper the code word, you decode, and you get M back. So this is for this variant of even Manso, but you can also get M plus delta, for instance, if you use a single key even Manso. And of course, that's really bad because M or M plus delta are very strongly related to M. So there is no hope that this will ever work. So this construction is trivial insecure, and why? Well, basically because of this related key distinguisher that we can use. In fact, there is a very strong relation between related key security and the non-malleable security of this construction. So that's what I'm going to show now. Basically, we can show that if you want to attack a cipher in a related key setting, you can use an adversary for the non-malleable code construction as a subroutine. So what would be the related key scenario? You have access to an oracle. Both we consider a strong setting. So you can encrypt and decrypt with an oracle with the key k and with the related key phi of k for a unknown key k, of course. And the related key function comes from some function set. And in one word, this oracle is implemented by our real cipher E, and in another, it's the Gothic cipher E, which is admin. And the goal of the adversary is to distinguish between the two words. So now if we take, we want to attack the cipher in such a setting, and to do this, we can use a non-malleable code adversary as a subroutine, as I said. So this non-malleable code adversary would take as a tempering function the related key function phi for the left part of the tempering, and the right part is kind of arbitrary, we don't really care. Then two messages M and prime. And the related key adversary can forge, not really forge, but using the related key oracles can create the oracle output that the non-malleable code adversary would use on such an input. So basically, we first get X equal to the encryption of M, then we apply the right tempering TR, and we do the related key decryption. And this is what the non-malleable code adversary would like to run on. So we just give this to this algorithm, so an input T, M prime, and this Y. And then we wait for the answer, and we can use this to distinguish in the related key setting between the ideal and real world. So basically, I'm not going to go into the details more, but somehow this shows that you can up-bound the non-malleable code security by the related key security of the cipher that you are using. When the temperate function is this one. And So of course, well, maybe there are better related key security algorithms, but always you can use this strategy. So that sounds nice, but actually, well, it's not really enough, because we have a big problem with related key security. If you don't restrict the related key function space, well, then you have no security actually. So for instance, if you take the related key function that just maps the key to a constant 0, you can trivially distinguish all the time. So basically the bound I just claimed was nice, well maybe, is just a bound by the constant function 1. So it's not really useful. But it's not so bad eventually, because thanks to work by Benner and Connor in 2003, we know that for some related key functions we get actually meaningful amount of security. So somehow we have half of a bound. If the tempering, or equivalently the related key function, is unpredictable, for instance, then we have a nice bound for the NMC, depending on the related key security of the cipher. So we need the other half, and one way to do it, at least the way we did, was to basically default back to the single key security of the block cipher. So if we assume that now we have this nasty tempering function that just maps the key or the randomness to a constant 0, well then there is no related key security, but actually you can attack, if you want to attack now the cipher in a regular PRP setting, so single key, you can again use the non-malleable code adversary as a subroutine by creating all of the inputs you need using just one oracle query. And now because you know that the key was tempered to 0, it's a constant that you know, you can just decrypt yourself using code E-1 with key 0, give this to the NMC adversary. And so again now we have another bound, but this time for just the PRP security. So that works well for this particular function, and you can extend if the tempering function is not exactly a constant, but basically it just maps to a few values, and all values have a large preimage set. So then that's where we need this graceful degradation security that I mentioned, because what you do is that basically you do the same as I just described, but on ciphers with their key spaces restricted to the appropriate smaller part of the key space. I don't think I will detail that. So we formalized this in the paper as a PRP with leakage notion, and that, well, together with the related key security bound allows us to have this result. So basically we have two bounds that are kind of always valid, and in some settings one of them will be really bad and the other is not so bad. And we can combine, and with this we can show that for any tempering function, at least one of the bounds gives a good security. And so we have this theorem, I'm not going into detail. And it's kind of tight, because we also have an attack that is basically a meet-in-the-middle attack that works with advantage t-square over 2 to the kappa. So we really have kind of a kappa over 2 bit of security for this construction. So just to finish, I mentioned a few instantiation issues. So if you want to actually implement this, what do you need? Well, you need a block cipher, well, with some related key security, sorry, and a PRP with leakage security. So on the related key side, there are not so many restrictions, but if you look at the details, you see that you can only use one related key query. Well, anyway, the short message is that, for instance, AS128 probably it works well, but then you just get 64 bits of security. If that's not enough, probably not, then you can go to Shackle 2. Then you get 256 bits of security for 256 bit messages. And if you want to encode messages that are longer, then probably the way to go is to use variable input length block ciphers. For instance, Mr. Monso Burrito. But then we need related key security for these. And actually, well, I'm not an expert, but I don't know if there are generic construction of VC with built-in related key security resistance. So if you know any, then maybe you can tell me. So that's it. Thank you.
Thank you very much. Any questions up here? I have a good question. So you made quite some performance improvement. Do you think there is kind of a lower bound where you can't go below? Are you very close to this, or do you think you can still make this more efficient?
Efficient in terms of what, like the code word size, for instance? I don't know.
Thank you very much. Thank you, speaker again.